Hi, my name is Daniel Carranza. I am going to be entering my fourth year here at Western, the host school for math and computer science. Today, I want to talk to you about formal verification of mathematics. So let's just jump right in. So first things first, I'm going to explain what you're seeing here. This is the Lean theorem prover, or at least the Lean theorem prover through Visual Studio Code. What is the Lean theorem prover? It's a proof assistant software. What that means is that it's a software that comes with some language and syntax that allow us to write mathematical proofs, right? We can prove mathematical propositions using Lean, using its syntax that it provides. And then what it will do is it will take these proofs and it will check them against an internal set of axioms. These axioms go back to the kind of our foundations of mathematics. And what that means is that when we write proofs and we put them into our proof assistant, Lean can ensure that these proofs are 100% correct and they're kind of formally verified to be all okay. Our goal today is going to be to formally prove that every natural number is even or odd. So in other words, we're going to take a kind of regular informal math proof and we're going to put it into Lean to ensure that it's 100% correct. So to start off with, explaining a little bit about what you're seeing on the left here is the code view, and on the right is the info view. So this is, the left is where we're going to type things, and on the right is where Lean is going to talk back to us. For example, I have this print statement here that will just print something to the info view. And I can, of course, write code here, and Lean will tell me this is not a proof yet. So Lean will yell at us if we ever get anything wrong. Whenever Lean doesn't have anything to say to us, then we know that our proofs are correct. Lean has a couple predefined mathematical objects that are good for us. For example, we have addition, which we know allows us to take two natural numbers and return another natural number. Same thing, we have multiplication predefined in Lean, and Lean also has, some of our favorite natural numbers like 1 and 2. I don't know, I think there are some more natural numbers after that, but I'm not sure. So how are we going to prove things in Lean, right? Well, first we need to know how to be able to write propositions in Lean, right? For example, here we have a proposition. A proposition in Lean is denoted by this colon prop syntax here. So for example, 0 equals 0. This is something that we could prove in Lean. 2 is less than 3. This is something we could prove in Lean. And even a more complex expression like for all natural numbers a times 1 is equal to a. This right here, I'm going to make note of another bit of syntax in Lean. Lean doesn't use this kind of inclusion operator that you use in regular mathematics. Instead, it just uses a colon. This is just, I want to make note of that. So for example, 0, Lean's way of saying 0 is an element of the natural numbers is to write out 0 colon natural numbers. So now we have some of these built-in propositions, but maybe we want to make our own propositions. For example, maybe we want to prove that, maybe we want to be able to say that a number is even or not. We know in regular mathematics that we define a natural number n to be even if there exists a k, a natural number k, such that 2 times k is equal to n. So how am I going to put this definition in a way that Lean can understand? I'm going to start off with the def command. This starts off a definition in Lean, and I'm going to give my definition a name, is even. Now, this definition takes a variable, n, and I'm going to write colon prop to indicate this is going to be a proposition, and colon equals to actually signal the start of my definition. And this definition, I can write it almost exactly how I would in kind of symbolic mathematics. So I'm going to write, there is a natural number k such that 2 times k equals n. And this is a definition. I can check, for example, that if I write is even 0, right? This is a proposition, right, that 0 is even, that we could prove. So we know how to write propositions. How do we prove propositions, right? Say we want to prove that 0 is even. A proof in regular mathematics might look something like this. We have to exhibit a k and prove 2k is equal to n. So in the case of 0, we have 0 is a natural number such that 2 times 0 equals 0. Shocking, I know. So how do we go about moving this into lean? I'm going to write the word lemma to indicate that I'm going to prove something. I'm going to give this lemma a name again, maybe 0 is even, right? And in order to say I want to prove this proposition, I write colon, and then I write the proposition I want to prove, is even 0. Then what I do is I write the keywords begin and end. This is our signal for lean to start entering proof assistant mode, basically. And when we're in proof assistant mode, lean is going to give us what our main goals are and any variables that we have in order to prove them. In this case, we don't really have any variables. But here, lean is telling us we want to prove that 0 is even. So in regular mathematics, right, first I exhibit the k, and then I prove that 2k equals n, or 2k equals 0 in this case. So in this case, I want my k to be 0. The way I tell lean that is I write exists I, and then I give the k that I want 0. Now lean has updated our goal. Now all we need to show is 2 times 0 equals 0. In this case, we know that this is true just by the definition of multiplication. In lean, the way that we say this is with the keyword reflexivity. And so there we go. This completes our proof. This is our first formally verified proof. We can now say with kind of 100% certainty down to the very first axioms of mathematics that 0 is even. If I write, say, check, and I give the name of this proof, right? This lean tells us this is a formal proof that 0 is even, right? Now let's do the same thing for odd numbers. We can write out a definition of odd numbers very similarly to how we did it with even numbers. I'm going to write def to indicate a new definition. I'm going to call it is odd. And I'm going to take a variable n. Again, I write colon prop to indicate that I want to define a new proposition. And the definition of this is very similar. This time, there exists a natural number k such that 2 times k plus 1 equals n. Now, if I want to prove maybe that 1 is an odd number, right? A proof in regular mathematics might look something like this, right? We have 0 is a natural number in n, and 2 times 0 plus 1 equals 1. So this is going to be a very similar process for moving this proof into a formal proof in lean. I'm going to write the keyword lemma to indicate I'm starting a proof. I'm going to call this 1 is odd. And this is going to be a proof that 1 is odd. Surprise, surprise. I'm going to use the keywords begin and end once more. Lean once again tells us what our goal is. So I want to set 0 to be the k that I'm looking for in this definition. Again, that's exists I, and then 0. And now I want to show that 2 times 0 plus 1 equals 1. Again, if we just follow the definition of multiplication and addition, we know that this is true. So I'm going to write reflexivity once more. And now I have a completely formal proof that 1 is odd. Wonderful. Now let's try to move on to more of a meatier proposition. So say I want to show that for every natural number n, if n is odd, then n plus 1 is even. In order to do this, a proof in regular mathematics might look something like this, right? First, we fix a natural number n, and we suppose it's odd, right? Then we want to use our definition of odd, right? If n is odd, then we can instantiate a k such that 2k plus 1 equals n. Then we want to exhibit the k that we're looking for in our definition of even, right? We want to say, so we're going to exhibit k plus 1, and then we need to show that 2 times k plus 1 equals n plus 1, right? This is just the definition of is even n plus 1. And you do that kind of through this chain of equalities here. We know multiplication is distributive. We rewrite plus 2 as plus 1 plus 1. And then we substitute 2k plus 1 for n above here. So this is kind of a complicated proof. So let's see how this breaks down in lean. So I'm going to introduce lemma for a new proof. Let's call this odd, then even. This is a proof that for any natural number n, if n is odd, this implies that n plus 1 is even. I'm going to use begin and end to signal the start of my proof. So our first step here in our informal proof is fix n in n. The way that we do this in Lean is we use the word assume. So we write assume a natural number n. Now we suppose n is odd. This, again, we can use the assume keyword. But this time, right, we want a proof that n is odd. And we're going to give this proof a name, say p. So now Lean has updated our context. Now we have certain assumptions that we can take advantage of, right? Mainly a natural number n and a proof that n is odd. So over here in the informal proof, right, we kind of unfold this the definition of oddness to get a natural number k and this equality here. In Lean, the way we do that is we use the word destruct. So we're going to destruct the proof that n is odd, and what that allows us to do is that allows us to assume a natural number k and a proof that 2 times k plus 1 equals n. We're going to call this proof q. Now, our goal is to show that n plus 1 is even, using all 4 of these assumptions that we have here. So the way I want to do that, right, I want to use k plus 1 as the number I need to multiply by 2. So that's, again, exists I, k plus 1. And now the last thing I need to show is that 2 times k plus 1 equals n plus 1. This is a kind of complex chain of equalities, and for that, Lean allows us to use the calc command. So we write calc, and then I'm going to start writing out, right, 2 times k plus 1 is equal to 2 times k plus 2. This comes to us because we know that multiplication is distributive. In Lean sort of has a couple lemmas and theorems about multiplication, in particular that it's distributive. In Lean, the name of this distributivity proof is mul_add. And then we give it our arguments 2, k, and 1. Once we're here, maybe let's format that. Once we're here, right, we just want to write plus 2 as plus 1 plus 1. And this comes to us just by definition of plus 2. So we can take advantage of this reflexivity keyword again. And now to finish off our proof, we want to substitute n for this 2k plus 1. And that comes to us from this equality q here. So I want to say this is finally equal to n plus 1. And the word for this is by subst q. This means that we're going to substitute this equality q into our expression here. And there we go. We now have a formally verified proof of this kind of complicated expression, right? Now, in regular mathematics, if we have such a proof for all natural numbers, right, we can definitely prove it for a single natural number. So, and we can do the exact same thing in Lean. So I'm going to write odd, then even, right? We just check this as a proof that for every natural number, if n is odd, that implies n plus 1 is even. So I can instantiate that at, say, 1, right? Now this is a proof that if 1 is odd, then 1 plus 1, which is 2, is even. But I actually have a proof that 1 is odd, right? And in kind of regular mathematics, we know that if P implies Q and P is true, then Q is true. We can do this exact same thing in Lean. So I'm going to substitute my proof that 1 is odd, and this gives me a formal proof that 2 is even, right? I didn't have to make a separate proof of this. This just comes to us from sort of the proofs that we have already predefined. If I want to prove, for example, that for all natural numbers, there's a kind of similar analog, right? That if n is even, then n plus 1 is odd. A proof of that is going to look very similar. I'm going to not go over it, but it's almost exactly what you would see in the above proof. But now what we're going to do is we're going to take these two lemmas and we're going to move on to our main theorem, right? We want to show that every natural number is either even or odd. Now, what might a proof in regular mathematics look like, right? First, we're going to fix a natural number n. And then what we do is, this is going to be a proof by induction. I'm just going to assume that you guys have seen proofs by induction before. this is kind of a complicated thing, right? I mean, in most first course, in most like logic courses, kind of for undergraduates, this is kind of one of the later things that gets covered. So we know this is kind of going to be a complicated proof, kind of. So for this proof by induction, we're going to start off in the base case that n equals 0, right? For n equals 0, we want to show that either 0 is even or 0 is odd. But we know that 0 is even, right? We proved it before. And then what we do is we fix n, and we suppose that this statement is true for this n, right? What does that mean? That means that either n is even or n is odd. And we continue this proof by case analysis, right? If n is even, then we know n plus 1 is odd by the previous lemma. So in particular, n plus 1 is either even or odd, right? And if n is odd, then we know n plus 1 is even, again, by a previous lemma. So by the principle of mathematical induction, this would give us that every natural number is even or odd. Now, how do we put this theorem into Lean? I'm going to write theorem. This is kind of this is another keyword. It's like lemma, but more important. We'll call this maybe even or odd. And this is going to be a proof that for all n, for all natural numbers n, is even n or is odd n. This symbol just means or. Right, so now, first I fix a natural number n. That's assume n. Then I want to proceed by induction on n. In Lean, this keyword is induction n, and I'm going to write with NIH here. I'll get to that in a second. But this splits up our goal into two sub-goals, right? First, my base case, and then my inductive hypothesis. So now in the base case, I want to prove in particular that 0 is even. So I'm going to prove the left side of this or statement, right? And now to give a proof that 0 is even, all I need to do is use the keyword exact to substitute a proof that I used before, right? Exact 0 is even. And now all I'm left with is my inductive hypothesis. We notice that we have two variables already, n and IH. This is where these come from. Whatever I name them in here, so for example, maybe I could name it K and inductive hypothesis. And this would be the names that show up for my inductive step. So if I want to, so then the next step in the regular proof is to do case analysis on my inductive hypothesis. The way I do this in Lean is I use the word cases. So I write cases inductive hypothesis. And now I have two cases that I have to prove, right? In the case that K is even, and in the case that K is odd. So now, in the case that K is even, I want to prove the right side of this or statement. So I'm going to write right. And now, if I want to supply a proof that K plus 1 is odd, I want to use my previous lemma. I'm going to write exact, even, then odd. That's going to be this one here, right? I want to instantiate it on a natural number K, and I need to supply my proof that K is actually even, which is our inductive hypothesis in this case. And now I'm left with one final case, the case that K is odd. It's a very similar situation. I want to prove the left side now of this or. So I write left, I write exact. I want to use my lemma that odd then even, instantiated at K with my inductive hypothesis. And that's it. We're golden. This is a formal proof that every natural number is either even or odd, that we can ensure is 100% correct by sort of the very first axioms of mathematics. Yeah, I think I'll stop here and ask if there's any questions.
I have a question.
Yes.
So what's the difference between theorem and lemma? You did say that theorem is a little bit more important, but like in what way?
So for most purposes, they are kind of the same by the in Lean's internal mechanism. They kind of really are the same. Lean provides them both, more than anything just to improve readability for users. So we have, but as far as lean goes, in fact, even definition, right? This keyword def, all the way up here, lemma and theorem are all the same, because it turns out they're all going to compute down to the same object in lean's internal structure. We have a message in the chat. Does lean work using set theory under the hood, or does it instead assume objects such as natural numbers? That's a very good question, actually. It actually doesn't use set theory under the hood. It uses something called constructive type theory, which is something you can ask me about later if you're interested in. But it turns out that this constructive type theory can recover a lot of set theory, which is what allows us to sort of use these very similar proofs to what you would do in regular mathematics. But that's a very good question. Thank you.
Nice. Just in terms of constructive type theory, does that allow this kind of a program to work with really abstracted objects like the category of propositions or like monads and build those kinds of objects very easily?
So I know that I think it partially depends on what kind of type theory you're working with. It turns out there are a lot of different kinds of type theory. There are a lot of different type theories out there. And certain ones sort of lead to kind of natural, easy things to define and sort of difficult things to define. I do know that there are things like, you know, kind of categories of, like propositions are sort of treated as their own thing, and there's there is like category theory defined in lean and lots of other things. I don't know if that answers your question, but
it does. Thanks.
Does it say anything about the axiom of choice? The axiom of choice has a kind of different interpretation in constructive type theory than it does in sort of lean, but in general, you know, the foundations of lean, just like in set theory, they don't exactly prove or disprove the axiom of choice. Kind of in logical system, the axiom of choice is once again independent in this system. So can it be used with? Yes, it can. In fact, everything we've done here is actually, all the proofs that we've exhibited here are constructive proofs that use intuitionistic logic. Lean's inner workings, which are constructive type theory, is also called intuitionistic type theory. So everything works here. Lean does have support for classical logic, but this is sort of tacked on. Lean natively works in intuitionistic logic.